Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for these students. Just pray that you'd help us to glorify you in what we do this day. In my prayer, Lord Jesus. Amen. So I'm a little bit sick, but I will try to do some examples for you. So basically today I want to talk about undetermined coefficients, with or without method of annihilators, so probably the first context I had the pleasure of teaching this material was when I taught Calculus 2 at NC State a few years ago. In the Calculus 2 course at State, we were expected to teach second order constant coefficient problems and the non-homogeneous case even. Now we don't usually do that here these days, but you can do that by just basically introducing some heuristics. So like for example, suppose we wanted to solve y prime prime plus 3y prime plus 2y equals t squared plus 1. All right. Now here's what I would have told my Calc 2 students. I would have told them, well, if you look at the forcing function, right? If you take derivatives of this, you either get stuff like t or like 1, and of course you got t squared to start with. So basically the only kinds of things you have from differentiating it or looking at it are just t or 1 or t squared, right? So it seems to suggest then that I should make my particular solution a t squared plus bt plus c. So in other words, the particular solution, I'm just looking at the forcing function, the thing on the right-hand side, and what are its possible derivatives. Take a linear combination of those things, and that ought to do it. This is what I would call the naive guess. Now the naive method will get you a ways. It'll solve this problem. Let's work it out. So what's yp prime? It's 2at plus b, yp prime prime, just 2a, right? Then let's plug that into the given differential equation here. Let me give this thing and let me give it a name. Who says name calling isn't useful? Let's see here. Star. See, I made it famous. All right, then what? Gather our thoughts. We want yp prime prime, right? Plus 3yp prime plus 2yp. We want that to be equal to t squared plus 1. Okay? That was interesting. Oh well. The mic won't pick it up. They'll just think we're crazy. Which is a little bit true. See, yp prime prime then is 2a. Don't forget the 3 here, plus 3 times yp prime, which was 2at plus b, and then plus 2yp. Well, yp was just at squared plus bt plus c. Now, if you guys remember partial fractions from Calculus 2, the algebra we're about to do is pretty similar to some of the algebra that comes up there. So what you want to do is to collect stuff with t squared on both sides, right? So like let's see here, I've got t squared times what? 2a, yeah. Plus t times what? 6a plus 2b, anything else? No. Plus 1, which I'll just write for the sake of appearances. 1, got 2a, I got myself a 3b, and then I've got plus 2c, right? Now that's all equal to t squared times 1 plus t times 0 plus 1 times 1. I'm just rewriting t squared plus 1 in a somewhat suggestive way to suggest to you we have two polynomials, we can equate their coefficients, right? So this guy has to be equal to this guy. This one, the coefficient of t has to match the coefficient of t. The coefficient of the constant has to match the coefficient of the constant. So 3 equations, 3 unknowns. But even though you guys have not all had linear algebra, you can do it because this is high school algebra. Or if you live in another country, middle school algebra. It's weird. It's weird how people all over the earth can do math before American children can. I don't know what makes American children so different. It's almost like their parents are lazy. Or their teachers are dumb. You pick it. You pick it. Or maybe American children are just stupider. I don't know. But I don't want to believe that because I think I'm American. I don't know. My children tell me I'm American. They tell me that they're only half American. It's like, I don't think that's how it works. Okay, so I'm going to start with we got 2a. So we got 2a equals to 1. A is 1/2, right? Let's see here. We've got 6a plus 2b is equal to 0. Therefore, b is, well, we can divide by 2, right? This gives us b is minus 3a, which is minus 3/2. And then I get 2c plus 3b plus 2a is equal to 1, which tells me that c is equal to 1/2 minus 3/2 b minus a. See what I did there? Just solve for c. But I know a and b, so I can make that a number. So this is 1/2 minus 3/2 minus 3/2 minus 1/2. The halves cancel. The halves have not. Let's see here. Oh, 9/4? Yeah. Okay. So we've done the work here. And so what we find hence yp equal to 1/2 t squared minus 3/2 t plus 9/4 solve star, right? So that's how we find a particular solution in this case. I didn't need to do, anything with annihilators to do that, right? Now that's not the general solution. What's the general solution? Remember the general solution? We had a theorem, which in this context says what? The general solution is c1y1 plus c2y2 plus yp, where yp is any particular solution, and we have y1 and y2 solve the homogeneous version of star, y prime plus 3y prime plus 2y equals to 0. We talked about how to do that. So this is the general solution theorem as it applies to our particular context here, I should say specific context. So what are y1 and y2? We can look at the characteristic equation lambda squared plus 3 lambda plus 2 equals to 0, which is lambda plus 1 times lambda plus 2. So we get characteristic values minus 1 and minus 2, y1 e to the minus x. X, good grief. Don't do that. Please don't do that. It always makes me sad when I see differential equation students not recognize that the independent variable has to stay the same through the whole problem. So don't let me do that. E to the minus 2t. And so finally, the general solution to our problem, y c1 e to the minus t plus c2 e to the minus 2t plus that particular solution. There you go. So it's a moderately difficult problem. I wouldn't think it's that hard, but now we could make it a little bit longer. What else could we do? I could give you a set of initial conditions. If I give you initial conditions, where should you apply them? Should you apply them to the particular solution? Should you just apply them to y1 and y2? Where would you apply initial conditions to? So this is where words are helpful. The general solution is what it sounds like. That's supposed to cover all possibilities in the solution set. So you'd want to apply it to the general solution. You may or may not be able to fit initial conditions. I mean, I don't know. I mean, here, if I'm really lucky, here I'll make it happen. Check it out. So y of 0 is 9/4. Y prime of 0 is minus 3/2. If I give you those initial conditions, right, that would make C1 and C2 be 0. Because I can get 9/4 from this when I plug in times 0, and when I differentiate it, well, that gives me minus 3/2, right? So those initial conditions will make C1 and C2 be 0. That's a possibility. But there's all kinds of other possibilities, right? If I make y prime of 0 not 3/2, if I make it, say, 2, and then I make y of 0, 0, then how would we do that? Well, so if I do y of 0, 0 and y prime of 0, 2, this will give me, y of 0, 0 gives me 0 is equal to C1 plus C2 plus 9/4. And the y prime gives me 2 is equal to minus C1 minus 2C2 minus 3/2, right? And you can solve those to find out what C1 and C2 are, all right? I'm not going to do that. My energy is limited. I need to save it for other things. Okay, any questions about this? Did you guys have an idea about what the naive method is? Let me try it out for some other problems. Suppose same thing, but instead of t squared plus 1, or let's say, suppose you have t squared plus 1 plus e to the t. What would you do? Everything you did before, and then you just add dE to the t, right? Superposition says that everything I did already will still go through, so I'm still going to find a half, minus 3/2, and 9/4 for ABC. So I can think about the e to the t term separately, right? I can just call this thing yp2 maybe. Right. Call this thing yp1 for the sake of discussion. So this was yp1 now. And excuse me. We can figure that one out much, much faster. let's see here. So we have yp2 prime prime plus 3yp2 prime plus 2yp2 is equal to e to the t, right? But when you differentiate d e to the t, what do you get? d to the t, 3d to the t, 2d to the t. So you can cancel off the e to the t's if you want. And that gives us 6d is equal to 1. So d is equal to 1/6. And so, just to summarize, y prime prime plus 3y prime plus 2y equals t squared plus 1 plus e to the t has solution y equals to c1 e to the minus t plus c2 e to the minus t, 2t, right? Sorry. Plus 1/2 t squared minus 3/2, right? We're using superposition because we know that when we plug that in, it produces t squared plus 1 from this differential equation, right? And then we know if we put in 1/6 e to the t, well, that pops back out e to the t after we differentiate as instructed by the y prime prime plus 3y prime plus 2y. And there you go. That's the general solution here. All right? Again, the naive guess. Yeah.
Now the d here is totally different from the d operator.
Oh, right. This is just a constant. Yep. Excuse me. That's going to happen. Oh, yeah, I'm out of tea. All right. So what if we up the ante a little bit more here? And, well, at least I don't want to scrap this one entirely. But let me just get straight to what will get us into trouble. In fact, let me stick with this differential equation, but get rid of all this. I'll leave this here, actually. I'm just going to... So suppose we have e to the minus t here, right? So the naive guess would be that yp is like a e to the minus t. But why won't that work? Because we know that what happens when you plug in e to the minus t, it's one of the solutions to the corresponding homogeneous problem. It's just going to give you back 0. Right? So the sort of ad hoc method is just say, oh, okay, so then I multiply by t. So, okay, so no can do. It overlaps. So instead I try yp is equal to a t e to the minus t. All right. Now that's exactly the same thing that would be suggested to us by the annihilator method, right? So let me just show you that. So like this, of course, it translates to d plus 1 times d plus 2 acting on y equals to e to the minus t, right? But you know, I hope, that we can annihilate. And so the goal of the annihilator is to find the smallest one that does it for you. So in this case, d plus 1 you can't beat. D plus 1 on e to the minus t is 0, right? So we can use a equals to d plus 1 in the method of annihilators. And so we get d plus 1 squared times d plus 2 acting on y, d plus 1 acting on e to the minus t. But as, the whole reason we did that was so that that becomes 0. Now this is a constant coefficient problem, right? And we know how to solve this. We know that the solution to this, we have basically characteristic values. Lambda is -1 2 times, right? And we have lambda, the characteristic value, -2 1 time. And so you know that the general solution to this homogeneous problem is something like C1 e to the minus t plus C2 t e to the minus t plus C3 e to the minus 2t. All right? But being that we've been working on this differential equation a little bit, you recognize immediately that this, right, and that are just the homogeneous solution for the problem, right? And by the general theorem, the other thing has to be the particular solution that we're looking for. So this suggests to me that we make yp a t e to the minus t. Now the method of annihilators doesn't undo the work that has to be done. All the method of annihilators does for you is it tells you when you need to multiply by t and when you don't, if you follow it. All right? If we did the method of annihilators on the things I had up there before, we would have been led to the naive guesses. Just the same. Once you really understand this, you don't need to do the method of annihilators anymore. You just multiply by t. But the method of annihilators helps us understand where these t's are coming from and gives us a deeper understanding of the structure. So now that I have the particular solution, the form of it, I have to still do the work, right? We have to figure out what A is. How do we do that? Can I erase this because my space is limited? Yay, yay, yay. So, yp prime, I'll leave the a out front. I'll leave the e to the minus t out front too, okay? So I'm doing the product rule in my head. So that's 1 minus t. Yp prime prime, a e to the minus t, product rule in my head. Minus 1 plus t, that's from the e to the minus t term. And then minus 1, I think. You guys can check me on that because I kind of feeling like death today. Let's see here, t minus 2. So I don't trust my calculations that much. Okay, and then we plug them in. So 3y3. What? Doofus. All right, so this gives me a e to the minus t times t minus 2 plus 3a e to the minus t times 1 minus t plus 2y, which is 2at e to the minus t equals e to the minus t. By the way, if you try to solve the naive guess in this problem, right, what ends up happening is you get nonsensical equations. You'll get 0 equals 1. It's impossible. So, just a word of warning, if you're on a test or something later in here and you get 0 equals 1 in your algebra, maybe, just maybe, your guess isn't the right one, for the particular solution. That's a possibility. Now, if we did this right, the stuff with t on the left-hand side has to erase itself from existence because there is no t e to the minus t on the other side. And we can prove that we can prove that e to the minus t and t e to the minus t are linearly independent on the reals, which means that they have this wonderful characteristic that if you have coefficients like this, so many wonderful gadgets and gizmos that linear algebra gives to you if you're willing to learn it. This is one of them. So if you have linearly independent functions, then you can equate coefficients of linearly independent functions. So these are linearly independent functions. You could calculate the Wronskian of this thing, and you'll find out it's non-zero. So my point is, I've got no te to the minus t over here. What happens to the te to the minus t terms over here? A, right? Minus 3a plus 2a. Score. All right. What do you know? So all things work together for good. All right. Let's see here. Although I would not claim that this part of differential equations is part of the special revelation of God. I think non-Christians can do this too. Let's see here. E to the minus t. So what do I have? I've got minus 2a plus 3a, right? Anything else with e to the minus t in here? No, that's it. So this is identically 0, right? So it's not an equation at all. And this tells me, well, that's boring. A is equal to 1. Aw, man. Okay, fine. Anyway, long story short, why? C1 e to the minus t plus C2 e to the minus 2t plus t e to the minus t. There you go. That's your general solution. I know, as you read the book, if you're reading the book, you don't have to read the book. You just pay attention to me if you want. It's up to you. I don't say that in every class, but in here I pretty much tell you everything you need to know. I can't make that statement in most classes I teach, but here I'm pretty much comprehensive in lecture. Curses, what was I going to get to? Mind wandering, point escaping me. Curses. Oh, so chapter 4 in the book, right? I've assigned you guys problems out of 4.5, right? And stuff like this, right? Now in there's no method of annihilators, right? So how do you know when to put t and when not to put t? Well, they've got these huge page-long theorems in there that have all of these gory cases, right? There's S's and R's and things floating around, and you gotta like, I'm in this case, so I should try such and such, right? And that's fine, but my point is to you, we can sort of organically derive these things with the method of annihilators, right? Which is nice. So that's why I put parts of chapter 6 interspersed with the discussion of chapter 4, because I think it's healthy for you guys, and it saves you the trouble of trying to memorize this page-long theorem in chapter 4 to apply. Excuse me. Now, students can memorize that theorem, perfectly capable of doing it, but man, it's more fun to see how it goes here. All right, so here's another one. Suppose we have y prime prime plus y equals to t e to the t plus cosine of t. Okay, I'm going to take that e to the t and knock it back down. Knock it back down. Okay, that's still too easy. Let me make it cosh. There. That's better. Okay, so... Oh. Something I should tell you guys. Cosh and Cinch. Let's talk about Cosh and Cinch. So these guys really, if you have this, all right, where beta is a positive constant, then you can prove that y equals to cosh beta x and y equals to sinh beta x are solutions. That's pretty simple because y prime is beta sinh beta x. So see what happens when you twice differentiate them? In other words, we got what? In both accounts, we have y prime prime equals to beta squared y prime prime is beta squared times y. So these are both solutions to this differential equation. In the same way that cosine and sine are solutions to y prime prime plus beta squared, right? If I change that minus to a plus, I just erase the h's and put some minuses. Still true. Now, of course, the other way you can look at this is lambda squared minus beta squared is equal to what? Lambda minus beta, lambda plus beta, right? Equal to 0. So what would be our usual song and dance? We would say we got y1 e to the beta x and y2 equals e to the minus beta x. How are those the same as cosh and sinh? What is the deal here? How can we have these two different answers? Didn't I say solutions were unique in some sense? Let me show you. So if I have y, c1 cosh beta x plus c2 sinh beta x, all right? Let me make these b's. So b1 and b2, just constants. What's the definition of cosh? It's the even part of the exponential, right? What's the definition of sinh? It's the odd part of the exponential. Remember we talked about that the other day? Right? So if you just rewrite these, you have 1/2 of b1 plus b2 e to the beta x plus 1/2 of b1 minus b2 e to the minus beta x. And so you see, it's just a different way of expressing the same solution. See, this is C1, and this is what we'd call C2 in our usual approach. So it's just like, you just have options. You can either express the solution. Let me get the beta out of the question here for a second. Let me make this a little bit more down to earth for you guys. So for example, 5y prime prime minus 16y equals to 0, I can either go y is equal to c1 e to the 4x plus c2 e to the minus 4x, or I can do y is equal to b1 cosh 4x plus b2 sinh 4x. All right? So I want us to have this option. When you run across something like d squared minus beta squared cubed y equal to 0, you can prove that the solutions include cosh beta x, sinh beta x, all right? And then you know what? X cosh, x sinh, x squared cosh, x squared sinh. So basically everything we can do, cosine and sine, we can do with cosh and sinh for, instead of having d squared plus beta squared, having d squared minus beta squared. The analogy goes further. If you have, it's even true that if I have d minus alpha squared minus beta squared, like that, all right? In fact, it is true that y is equal to e to the alpha x cosh beta x and e to the alpha x sinh beta x are solutions. So you can go a long ways down this road. But anyway, that's just kind of like, okay, great, but wouldn't you rather just write, exponentials rather than products of exponentials and coshs and sinh? I mean, this is sort of just an academic curiosity, so I'll shut up about it. But I think it's worthwhile to use cosh and sinh for the pure difference of perfect squares kind of thing. And so something like this, cosh and sinh pay off. My point to you is it's fine to think about, so the reason I've given you this little spiel is so that I can use, rather than thinking about exponentials and annihilators, it gives me just another result for coshs and sinches. My point in all this, can I erase? Okay. Is that my point in all this is that as I think about, well, what would be the naive guess? Let's just put down the naive guess to start with. We just look at this and take derivatives. So derivatives of cosh gives me sinh. So I do a cosh t plus b sinh t, and then derivatives of cosine give me what? Sine, right? So plus c cos t plus d sine t. I'll put an e there. It's going to bother Luke. See here in just a second. I mean, that's a good way to be bothered. I'm not objecting at all. My point is that would be the naive guess, and it's half right. Let's see why. So to annihilate cosh t, use d squared minus 1. All right. To annihilate cosine t, we use d squared plus 1. Okay. So if you want to annihilate them both at once, what do? Do you add them, subtract them, multiply, divide? Well, divide is out. We don't know how to divide operators. People knew how to divide operators back in about 1920, but since then we forgot. So, no, it's true. There's his classic book, Ince Differential Equations. He's got all these formulas with division of operators. If you can interpret them in terms of truncating geometric series and do calculations here faster than I'm showing you. I saw a talk on it once. But it's kind of a dark magic, so I don't teach it. So this is d squared plus 1. We multiply them. D squared plus 1 times y equals to cosh plus cosine. Okay, so just you do a as the product of these. That's the way to do it. And you don't multiply them out, because that would be stupid. Because ultimately you're interested in... So then we annihilate this, and it gives us d squared plus 1 squared, right? D squared minus 1 y equals to 0. Taking a of both sides. And the overlap phenomena is reflected in the fact that, there is literally an overlap of the annihilator and the defining operator of the differential equation. So here L, right? This tells me that L is equal to d squared plus 1, right? If I want to write this as L of y in our language we were using the other day. So you see that there's this and this. They're the same, and that means that when you actually go to write this, the general solution here to the corresponding homogeneous, this problem, we get y is c1 cos t plus c2 sine t plus c3 t cos t plus C4t sine t, plus, and then here's what I'm advocating, C5 cosh t is a natural way to go here, C6 sinh t. You got choices. If you want to, you can, of course, I mean, you can convert everything to exponentials if it's so inclined. If you're so inclined, this could be d minus 1, d plus 1, you know, and that will give you an e to the t and e to the minus t. But I just think it's way easier to operate in coshes and sinh here for this problem, right? Which part of this is the homogeneous problem? Well, the homogeneous solution is this part, right? Here's the YH, the so-called homogeneous solution. And over here, the method of annihilators has given this as a template for YP. It's not YP yet because it only becomes the particular solution once we actually do the work to find the constants C1, I mean C3, C4, C5, and C6, but of course we don't want to use C3, 4, C4, and C6 because it's a real drag to write those more than once. So we replace them with ABCE as to avoid, let's see here, so A cosh plus B sinh plus C t cosine t. Oh, I did the cosh sinh first, sorry, whatever, I hope you can forgive me. E t sine t. And in fact, you don't have to do everything all at once. You can divide and conquer here. Right, we could do the cosh and sinh piece first. Let me call this piece YP1. Let me call this piece YP2. There's no sense in doing everything at once because it's kind of a pain. Right? So why don't we just take care of the cosh and sinh part first because it's easier. I'll feel better about my life after I do that. So YP1, what's YP1 prime? What's YP1 prime prime? I should give this to you before I forget. Let's see here. All right. So YP1 prime prime. Can I just go to YP1 prime prime? What's YP1 prime prime? Can you guys see it? Differentiate this 2 times. What do you get? Cosh goes to sinh, and then the second differentiation goes back to cosh again. Sinh goes to cosh, and then cosh goes to sinh again. So differentiating that 2 times gives me back, what does it give me back? It just gives me back YP1, right? Sorry, I'm tired of writing. Anyway, it's pretty easy to see that that's true. So if I look at YP1 prime prime plus YP1 equal to what? Equal to cosh t, right? I'm trying to get that piece of the forcing term right now. This is really 2YP1 equals to cosh t. Now, of course, you don't have to do things like I'm doing them. I'm just trying to save myself writing because I'm lazy. A cosh t plus 2b sinh t equals to cosh t. And good news, cosh and sinh are linearly independent functions. You see why I was using that? That's why we had that talk last time, is because I want to be able to say those words in here. And it does cost me a little bit at the start to explain what I mean by that. But once we have it, it's so useful. So the cosh and sinh are linearly independent. So that means I can equate coefficients. I got 2a is equal to 1, and 2b is 0. So a is 1/2, and b is equal. Now, if you doubt me, do you doubt me? If you doubt me about cosh and sinh being linearly independent, what could you do? Oh, we did that last time, though. We calculated the Wronskian of cosh and sinh, didn't we? Actually did that one. It came out the cosh squared minus sinh squared, I think. Anyway, you could do it. Okay, so what's YP1? YP1 is 1/2 cosh t, right? All right, that's half of it. Now let's figure out the other half. The other half, of course, is much more annoying because yp2 is, can we figure out any way to write that nicer? I'm trying to remember. Not really. Okay, so that's ct cosine t plus et sine t, right? So you differentiate that. You get c cosine t minus t sine t, right? Plus e times sine t plus t cos t. Differentiate 2 times yp prime prime, yp2 prime prime. That gives me a minus sine t minus t cos t plus e cos t plus cos t minus t sine t. Of course I can clean that up a little bit, right? This is really minus 2 sine t minus t cos t, right? And this is just 2 cos t minus t sine t. Oh, yeah. So one of the great luxuries of my independent studies this semester is I end up lecturing on the bottom part of the board in a rolly chair. It's a lot of fun. So I'm bringing that to this class. It feels good. Okay, so let's see here. yp2 prime prime plus yp2 is supposed to be equal to what? What are we trying to match now? Well, now we're trying to go with the cosine t. I'm using superposition to piece these things together, right? So I know that my 1/2 cosh t will produce the cosh t on the right-hand side, and I know that whatever I'm going to find out here will produce the cosine t. I add them together, I get the whole deal. Superposition. Okay. So this gives me c times minus 2 sine t minus t cos t plus e 2 cos t minus t sine t. See here, and then plus yp2. Ct cos t plus et sine t. All of that is equal to cos t. Now, this is just like the problem we worked with overlap earlier today, right? If this works, the stuff with t's ends up canceling. And of course, naively, you know cosine was going to fail, right? You knew that cosine and sine were going to fail, right? Fail because these are the homogeneous solutions, right? They produce a 0 when you plug them into the differential equation. Now, did the t's cancel like I wanted? Excuse me. Golly. Whew. I think they do, right? So this guy, natural enemy of this guy, natural enemy of that guy. Wait a minute. That guy, yeah. They're out of order, but... So what do we get? We get, from this, two things. We get minus 2c equals to 0, and we get 2e is equal to 1. So I'm equating the coefficients of sine and cosine there, okay? So sine x coefficients gives me this. The cosine coefficients give me that. So therefore, yp2 is just got the e term, and e is 1/2, right? Which is to say 1/2 t sine t. All right, I think we have all of the necessary ingredients. We can now construct the general solution. Let us do that. So I'll do it over here. So we have worked out that y prime prime plus y equals to cosh t plus cosine t has solution y equals to c1 cos t plus c2 sine t. Those are the homogeneous pieces. Plus, what I get? 1/2 cosh t plus 1/2 t sine t. And there you go. That will solve this problem for any set of initial conditions. And you see the difference. I mean, so like when there's overlap, you don't just multiply everything by t. You only multiply the offending part by t, right? Like the overlap is from the cosine, it's not from the cosh. So I didn't have to get more complicated with my cosh solution, just with the cosine part. So I've showed you guys the method of annihilators, so you have some sense of why this is true. You have to imagine yourself in a world where you hadn't been shown these things to see why it seemed. I mean, when I did this for Calc 2 originally, you know, students are like, but why? You know? So I'm just throwing the why in there from the start. So now, from another perspective, you're like, well, why are you showing me the method of annihilators after I do a few of these and I get used to it? I don't need to do the method of annihilators because I can just write down the right form for the particular solution and go about my business from there. Well, that's true, right? And that's where I want you to get to eventually. But I will also ask you on the test some questions like, what's an annihilator for this function, you know? So maybe we should let's just focus on that. I mean, it takes me a long time to work out a specific problem, but I think this should be more than enough to get you started on the homework from 4x5. You think it's fair? Yeah. I want to talk more about applications some other day, but I would just point this out. Y prime prime plus y equals to cosine t has the interpretation of, so this is like mass equal to 1, spring constant equal to 1, and we just found the solution like this, right? And so what happens as t goes to infinity? So this stuff stays bounded, right? I mean, whatever that is, if it's going between plus and minus 2, that stuff is going to still go between plus and minus 2. But what happens to the 1/2 t sine t term? It what? It goes to infinity, right? So what happens at spring? I mean, the mathematical model here stops making sense at some point, right? The spring breaks. This is an example of resonance. Resonance. Actually, this is sort of pure unbridled resonance. There's a more refined notion of resonance that we'll talk about in a future class, but it's kind of cool, right? Anything other than cosine t there, if you put cosine of 1.0000001 t, you know what? The solution does not have t in it. It's just a sum of sines and cosines. So anything except for, if I solve y prime prime plus y equals to the cosine of bt, we could solve that. Check it out. We'd say yp is a cosine bt plus big B sine bt. Differentiate that thing 2 times. Minus a b squared sine, good grief. Getting to the point, this gives you minus b squared yp, right? So therefore, yp prime prime plus yp is equal to minus b squared plus 1 times yp, which is equal to cosine bt. And you can even see there, something funny goes on with b equals to 1, right? As you look at this parameter. So I've solved not just one problem here, but a whole string of them by introducing a parameter, right? B is a parameter. Different choices of b gives you different differential equations. And you can see that b equals to plus or minus 1 is special, right? B is plus or minus 1. You can't solve that equation. That means that this template is insufficient, right? So this guess, or if you're German ansatz, fails. But otherwise, you put yp equals to cosine bt over 1 minus b squared, and you're good to go. And that's a particular solution. And it's bounded. So this resonance requires exact matching in this case. Was it?
So, this is describing a spring cosine t with force on the object.
Right, yeah.
Force applied.
Yeah, the cosine tu, this is the force applied, right? External force, right? Or the same is true for if you have you can have a voltage source and an LC tank. This also gives you the same sort of differential equation. There's no q prime term. There's just how's it go? L di dt plus q over c equals to E, Kirchhoff's law. So that's L q prime prime plus q over c equals to E. So you get q prime prime plus q over LC equals to E over L. And so there's also this, that's the corresponding LC tank problem. You also have this, if you have pure resonance, you can, you eventually burn things. Now, in practice, pragmatically speaking, this is not reality, right? Reality is that there is a resistor somewhere, right? And there's a friction force somewhere. Or B. There's a friction force in there, and so it's not quite that. There's a much more complicated question that we can ask, which is if you have my prime prime plus by prime plus ky equal to, for example, f naught cosine omega t, right? Then what choice of omega maximizes the amplitude of the particular solution? So this, by the way, the particular solution is also called the steady state solution in applications. The reason for that is that if you look at a differential equation like this, you've got ay prime prime plus by prime plus cy equals to 0, and